Alright, so in this video we're going to go over the different types of isomers and what a homologous series is and the properties of homologous series. So if you have a homologous series, it's going to be a series of compounds with the same general formula, but basically you just add a CH2 to it. So if I'm looking at methane, well then I have ethane, propane, butane, so essentially I'm adding another carbon atom to the chain. So it could also be something like methanol, ethanol. So it could have a functional group too. All you're really doing is just adding a carbon atom to that chain, and then it's going to be part of a homologous series. But it has to have the same functional group and the same general formula. So if you're looking at a homologous series, so if I go from methane to ethane to propane and I'm adding all these carbons, what I'm going to see is that the boiling point increases as I go. And that's because every time I add a carbon atom, I'm adding more electrons. I'm adding more polarizable electrons to create temporary dipoles to increase that London dispersion force. So it increases the intermolecular forces, and then that increases the boiling point. Now, something to note, because we haven't really talked about branching before, if you have a compound that it has branching and the same number of atoms, same number of all types of atoms, branching actually decreases the surface area. So if you decrease the surface area, you're going to create weaker London dispersion forces. So creating weaker London dispersion forces means the boiling point goes down. So let's say that I have something, or let's just do skeletal. Let's do this. So I have this is butane, and then I also can take the same thing, and this has the same formula, the same number of carbons, the same number of hydrogens. The difference here is that I have a branch, so in this case, this will have a lower boiling point because it has a lower surface area. Okay, so isomers. We have all sorts of isomers. So structural isomers are going to be compounds with the same general molecular formula or the same exact molecular formula, but you're just arranging the atoms differently. So each isomer is going to have its own unique chemical and physical properties. So if you have more atoms, you can have more isomers. So let's look at the alkanes. Okay, so we have methane, ethane, and propane. Well, all of those, you can only have one structure for that. So for methane, this is what it is. There's nothing else you can really do with that. It's just going to have 4 hydrogens attached to it. Same thing for the ethane. Each carbon is going to have 3. There's nothing else that can be done unless you actually change the formula, which means it's not an isomer. All right, so let's look at something else. So let's look at butane. So if I look at butane, butane has 4 carbons. Well, in order for it to be classified as an isomer, it has to have the same number of carbons, the same number of hydrogens, but it has a different arrangement. So I could take off the last part and then place it somewhere else. So I could place it in the middle like that. Those would be structural isomers of each other. They have the same formula, same number of carbons, same hydrogens, but they're placed differently. Okay, so let's draw for hexane. And you need to be very careful about this because a lot of people will draw what they think are isomers, but it ends up being the same thing. So the first one, let's go for the obvious. Draw the straight chain. 1, 2, 3, 4, 5, 6. Okay. So now take off one of the ends and then place it somewhere else. Where else can you place it? So 1, 2, 3, 4, 5. Okay. Well, I can place it here, right? All right. So then let's do the same thing. Let's take off the last part. Let's place it somewhere else. I can place it here. Okay. Let's say that I do this now. And then I place it here. Well, technically, this and this would be the same exact thing. How do you know, even though it looks different? Name it. So it has 1, 2, 3, 4, 5 carbons. That's the longest chain. And then remember, you number to give it the lowest possible numbering system. So 1, 2. So 2-methyl pentane. So go over here, do the same thing. Longest chain is still 5. And then you've got a substituent group. And then you're going to give it the lowest number possible. So you start numbering from this way. It goes 1, 2, So 2-methylpentane. It's the same thing. That's not an isomer. Name it if you're not sure. Name them. Okay, so now I've got 3. Well, let's see if I take off 2 pieces now. So 1, 2, 3, 4. So I took off the piece here, I took off the piece here. Well, what can I do with that? I can put one here, and then I have another piece. I have to do something with that, so I'm going to put it here. Okay, that's different. So let's do that again. Now, can I put 2 pieces anywhere else? Well, what if I put them both here? And then that would be an isomer. So there are 5 isomers, and then sometimes I see people do things like this. Well, let's say, oh, let's just take off another piece and then we'll make all the attachments here. That's way too many bonds. So just because you're trying to make isomers doesn't mean you can make any more isomers. So 2 things to watch here. Make sure you're not drawing the same structure again. Name them. And then the second thing is make sure that the isomer that you're drawing is actually possible. Do you have too many bonds? Do you not have enough atoms? Make sure. All right, so let's look at boiling point. Now, ethane or octane, which would have a higher boiling point? Well, octane has more atoms, same types of atoms too. It's all nonpolar, so it would be octane. Ethane or ethanol. Ethanol is going to have an alcohol group or hydroxyl, so that has hydrogen bonding. So it's definitely going to be the ethanol. Okay, why would 2-methylbutane have a higher boiling point than butane? Well, butane is this. 2-methylbutane is this. This one has another carbon. So this one has more polarizable electrons. It can have a stronger London dispersion force. All right, so which of the following would have a higher boiling point? 2-methylpropane or butane. So let's look at those structures. That's butane. This is propane. 2-methyl. This would be this. Well, this one has branching right here. Oh, I'm not trying to circle this, sorry. So this one has branching. So if we have branching, that means it has a lower surface area, so that means the boiling point is lower, so butane should be higher. All right, so the different types of isomers that you'll see are chain isomers. That's what we just looked at with the alkanes. So it's the same functional group, okay, but the chain is going to be different lengths. So I could have, let's say that I have, let's do this one, pentanol, okay. Well, a chain isomer could look like this. So it has the same formula, it's just the chain has different structure, but we have the same functional group here. Okay, so positional isomers would have the same functional groups, but they're present on a different position. So if I have butanol, so this would be butanol, 1, 2, 3, 4, like that. Okay, that's butanol. And then 2-butanol would be this. So it's the same number of atoms and the same functional groups, they're just in different spots. Okay, so a functional group isomer would have the same formula, but the functional groups are different, which changes the compound's reactivity and what it will do very significantly. So let's look at ethanol. This is ethanol. Well, methoxymethane would look like this. With the oxygen in between. So we have different functional groups, the same formula though. All right, so we also have some terminology that we need to make sure that we understand. Primary, secondary, and tertiary. So we could talk about primary, secondary, and tertiary carbons. We can also talk about primary, secondary, and tertiary functional groups. Okay, so a primary carbon is going to be attached to a functional group and then also at least two other hydrogen atoms. It could be attached to 3. Okay, so if I'm looking at ethanol right here, this would be a primary carbon. Okay, it's also a primary alcohol here. So if you have a carbon that's attached to at least 2 hydrogens, that's going to be considered primary. A secondary carbon is going to be attached to the functional group and then 1 hydrogen and then 2 other carbons essentially. So a secondary carbon is going to be attached to 1 hydrogen, a primary carbon will be attached to at least 2, and then a tertiary will be attached to 0. Okay, so the secondary carbon, so if I'm looking at this right here, if I draw that out, I have C, 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 and then I have an OH. Like that. Okay, so this carbon right here is considered to be secondary. Okay, it's attached to only 1 hydrogen. So a primary is going to be attached to at least 2. A secondary will be attached to only 1. Okay, so a tertiary carbon is attached to 0 hydrogens. So if I have this compound right here, I have a carbon in the middle, which is attached to CH3, another CH3, and then another CH3, and then it's attached to an alcohol, or a hydroxyl. So this carbon right here is going to be considered a tertiary carbon because it's attached to 0 hydrogens. So primaries are attached to at least 2 hydrogens, secondaries are attached to at least, or just 1 hydrogen, and tertiary would be 0. Now we can also talk about primary, secondary, and tertiary in terms of functional groups. Okay, so if I look at this compound right here, this halogen alkane, I have bromoethane, and it's going to be primary. This is essentially attached at the end, and then you can see it's attached to a primary carbon. Okay, this one, 2-bromobutane, is attached in the middle. It's attached to a secondary carbon because this carbon is attached to just 1 hydrogen. And then right here, this bromine is attached to a carbon that has 0 hydrogens, so it would be considered tertiary. So again, primary would be at least 2 hydrogens attached to the carbon. Okay. Secondary would be where we have 1, tertiary is 0. And then you can consider the functional group to be primary, secondary, or tertiary based on what type of carbon it's bonding to.